Alright, here we go. Stream started. Is it working, guys? Is it working? The acoustic may sound a little different today because I am in a little different setup. Sorry. Wait. Don't know what's wrong. Let me just drink some water real quick. So right now, I'm in the bedroom this time. Before this, I've been streaming in the living room throughout the past two streams. Today I decided to stream in the bedroom on the bed because I thought this would be a little lengthier stream, and my mom's gonna come home in like an hour, so I don't think I'd be able to like finish the stream in time that my mom comes home, because like I don't have a personal room per se. I have one, but it's not renovated. There's no air conditioner. There's no fan. And we don't really have the budget to get an aircon. So now I'm just kind of here. Okay. Let's see. Where can I promote myself? Where can I promote myself? Links? Does this work? No. I honestly kind of want to promote myself in this server because there's a bunch of nerds in here. I guess not. There's no self-promo channel. Time to find a different channel. Okay. Let me just send it to this one. Alright, and yeah, also I should tweet it, yeah. How many people are in right now? 0 viewers. That's alright. Whoop. Pose, Alright, tweet. There we go. That should be all the everywhere that I want to post. Alright, so today we're in a little different setup. I'm on the bed because, okay, so what the fuck was that sound? I just heard some sound that normally happens when some audio device change happened. Did my microphone just suddenly explode? Is it using the right mic? It is using the right microphone. Okay. Well, good. So normally my mom gets home in like an hour. I don't know if I can finish the stream in an hour. So normally this is my room. This is the room I'm in right now. This is the closet. And so this is the bedroom. This is not to scale. The closet is actually a little less wide. So my room looks kind of like this. This is the plan of my room. Not my room, what am I saying? It's like our room. My mom and mine, and then there's also my brother's. Yeah, it's where we live. Yeah, the room in which we live. And so this is the door that I normally open. Before this, there's a small little table that I used to stream on. This was from the previous streams, but considering the fact that my mom is probably gonna come home, she's gonna open up this door and then she's gonna get jump scared by me streaming over here. And so I decided to move over to the bed over here, which is not like that. Hold on. There's also the closet that's sitting right over here, not drawn to scale, and there's the bed over here. Just like the general layout of my room. And so when I stream, before this I was streaming over here, but now today I'm streaming on the bed right here. I'm streaming on the bed right here because my mom, once she comes in, she doesn't look in here. She probably does her own thing over here doing her job. Yeah, which means that even though she comes home early, it wouldn't be distracting me. So that's that. I should check my YouTube channel on my phone. Yeah, there we go. Alright, okay. Now I have it set up. I see myself on my phone. I can consistently check chat now. So, time to start doing homework. Today we're doing homework on... Today, it's actually a blend of two homeworks, because I didn't do one of them because it was fairly difficult. But I had an epiphany the other day that made me able to solve it. So, yeah. So we have two subjects today. First, we're doing differential equations, which is much easier. It's much more straightforward. It's mainly just learning how to use the same technique over and over. Hello, Hanyan. Welcome to the server. Not server. What am I saying? Welcome to the stream. Differential equation, and then we also have advanced calculus, which is a little more difficult. So, bitches. Okay, there we go. Okay, there we go. The chat is showing up. Welcome to the stream, Neon. How are you doing on this fine day? So yeah, differential equation with an S and advanced calculus. We're doing differential equations first. Advanced calculus, we'll do that later. At the airport right now. Oh, right, you're on a trip. Are you gonna be, like, at the airport? You mean like you're returning home? Or are you like going on a trip to a different country next? I'm coming back home. Yes, nice, nice. We're gonna be able to see Neon stream now, right? Once you're home, you can stream, and then you can get subscribers and shit. Hello, Ishkanami. Welcome to the stream. So we're doing this one. First differential equation should be straightforward. Dude, if I can hate the airport so much. Yes, maybe we'll see. Yup. It would be cool if you stream, I guess. Alright, so this differential equation, I'm gonna rewrite it as d by dx, dy by dx plus y equals to e to the power of x. So, how do we solve this one? This differential equation is a, what's it called? I don't know what's it called. Exact differential equation. This differential equation is an exact differential equation. What we do is, at least it's not Florida's airport. That's just like the PUBG lobby when it first came out. I've never been there, but I mean, like, never been in the PUBG lobby when it came out, but like, god damn, that is a very descriptive and specific way to put it. This differential equation, you can write it as, okay, so okay, the method to solve this kind of differential equation is that we are gonna need to find some function. We're gonna need to find something that would let us write it as f of x and y. We're gonna have to find something that would solve, that would make it look like this, equals to g of x. We're gonna have to find something that would transform this form to this form. And once we have this form, we can turn this into an integration. We can then turn this into an integration problem. It was honestly fine. I've been there before, and let me tell you, it was honestly fine. Why did you send that twice? Did you send that twice? Yep, that's internet, alright. Today I've also noticed my internet is a little bad today. I don't know why. Like, it took a little while to load pages and shit. But overall, I think it's okay. And they're about to ruin my stream. There are people call. Why is there USB sound going on again? Did you guys hear that, or was it just me? Alright, so how we can solve this is what we do is we find some value known as the integration factor mu, right? We find an integration factor mu that is a function of x such that once you multiply it like this, right? Such that once you have this form, you're gonna end up, you can turn this into that other form. So how do we turn that into this other form? Well, we know that this one looks almost like this for this whole equation thing looks almost like the product rule. You remember the product rule? If we have this guy and this guy, the product rule in calculus, what we do is we turn this into a sum. We turn this into addition of two terms. The first term is going to be the derivative of mu times the normal value of y, and then you add it to the normal value of mu times the derivative value of y. Now this whole thing already lines up with this expression, almost, because you can see that we have this term already, and then this term and this term almost the same. It's just that here mu prime, and it's just that here mu is replaced with mu prime. So we have to choose a certain value of mu such that these two would be equal. And that value of mu is mu equals e to the x. I'm gonna like generalize this on the next once we're done with this question, but for now I'm just gonna give you an example to give you the idea. So if mu equals e to x, let's see what happens if we multiply the whole equation by this. If we multiply the whole equation by e to the power of x, right? We're gonna have e to the power of x y primed, which is derivative of y with respect to x, and we have e to the power of x times normal y, and it's gonna be equal to, on the right hand side is e to the power of x, so it's gonna be e to the power of x squared, which is gonna be equal to e to the 2x. Let me just write that better. Which is e to the power of 2x. Alright. So yeah, how's the by the way, how's the sound today? Is it like more muffled? Because it looks like it would be a little muffled because I actually have to like set up a whole ass pillow fort to like, so like my fan is over there. My fan is like behind the computer screen right now, and it's blowing towards the microphone. So I had to like set up a whole ass, well, not a whole ass, I just had to set up a pillow for it to like protect my microphone from being, you know, blown by to protect my microphone from being blown into, no, to protect my microphone from the wind from the fan. Yeah. So yeah, if I don't have it, it would sound like, I don't know if I can move it. I should not move it actually. It would sound like something like did that work? Can you hear that? Alright, anyway. So the left hand side here, this whole thing becomes what? It becomes the derivative of e to the x times y. Equals to e to the 2x. You can verify this. You can verify this. That you can verify that this expression and this expression is equal. Let's just do it. We might as well do it. D by dx of e to the x y is equal to d by dx of e to the x times y added by and then you add it to d by dx y times e to the x. And what you're gonna end up with is gonna be e to the xy plus y primed e to the x, which is exactly the same as this one. It's just swap the orders around. I should not have done that. So yeah, this is indeed true. We can indeed transform this expression to this one, which we can now integrate. Remember this? How this is like a separable differential equation? What we do is we integrate both sides by dx. So we have d by dx e to the x times y, and then integrate this whole thing with respect to dx. Airport Wi-Fi is legit horrible, so I'm gonna be cutting out a lot. Yeah, it do be like that. Airport Wi-Fi, it tends to suck. You could probably catch up on the stream on the plane, right? Okay. So yeah, the left hand side you integrate something that you took the derivative of, which is just gonna give you the same thing again. E to the xy plus some constant c. This is just the fundamental theorem of calculus. You know, take the derivative of this expression, and then you integrate it. You get the same expression with some constant. On this side, we have e to the 2x dx. Once you integrate this, you should have 1/2 e to the power of 2x, which you can add c to that, and then I grab the eraser tool, and I delete the c over here. Consider it good enough. And then we're gonna end up with y equals to 1/2 e to the x plus c times e to the negative x. And this is our answer. And this is our answer to the problem. Y equals to 1/2 e to the x plus c e to the negative x, where c can be anything. Yeah, whatever c is going to satisfy this equation. So obviously I'm going to check first if that is true or not by just doing it. Y prime is going to be 1/2 e to the x minus c e to the negative x. And then normal y is going to be 1/2 e to the x plus c to e times e to the negative x. You add them up and you get e to x. So so here y prime plus y equals to e to the power of x, which is the original equation. Yay! I should not have watched Final Destination before getting on board. That's why. Why would you do that? Why would you do that to yourself? Why would you do that to yourself? Ah, well. Alright, well anyway, that's our first problem done. Fairly quickly, compared to, the previous streams. We're like only 20 minutes in. Okay, so allow me to explain this, the general formula. So in general, what we would have is we would have something like y primed plus p, which is a function of x, times y, and this will be equal to something like qx. And we're gonna generalize this to be for this example, p is 1 and q is e to the power of x. All right. So to generalize, what we want to do is we want to find a something that would make this whole expression be some sort of a function that, yeah, that you can turn into a can combine using the product rule, which means if I multiply both sides by the integration factor mu of x, right? We multiply by mu of x, we're gonna have mu of x, p of x, y equals to q of x, mu of x, which we don't know what mu is just yet. What we need to find is we need to find mu. So we want to make sure that this thing fits the format that d by dx of mu of x times y. We want to make this whole thing fit into this format, which means the product rule, we already have this term. I circled in red, but here we don't have the term that is underlined in red yet. So what we have, no wait, we have the term that is underlined in red, is this one, but we don't have the term that is circled in red. This term must be equal to this term, which means mu x times px must be equal to mu prime. Therefore, mu prime must be equal to, hello Tessie, welcome to the stream. That means mu prime must be equal to mu x times px, which means we can bring the mu over to the other side. We can bring mu over to this side. So we have 1 over mu x, and there's going to be d mu x. I'm just going to remove the d mu by dx. There's going to be p of x, which means we can integrate both sides with more physics. Yep, this is my life now. I opted into this. So what we do is we integrate both sides with the equation. This one becomes 1 over mu d mu. This other side becomes p of x dx, and we integrate it. What we have is we're gonna end up with natural log of mu must be equal to the integral of px dx, which obviously if you exponentiate both sides of the equation, we get mu equals to, we get e to the power of natural log, so the left hand side would become just mu. On the right hand side would be e to the power of integral of px dx. And this is what is known as the integration factor. Yeah, this is the integration factor. We plug this back into this one. We plug this thing back into the equation. We're gonna end up with d by dx equals to qx times mu of x, and then from this we can solve the equation normally. Yeah. So let's just so we're gonna go ahead and do that, exactly that. We use this one is 29.7 for an A4 paper, and then I grab the next question. I copy and paste it here, and we have this. Have I mentioned how I have Blaha now, or what it was called? What's it called? Like the IKEA shark. Is it pronounced Blaha? It sounds like it's like. Hold on. I've heard someone pronounce it differently, so I'm not quite sure. Swedish pronunciation. What? Name Blaha, IKEA's blue shark plush toy, is generally pronounced blowhigh. Oh. Although Swedish pronunciation is closer to blowhigh or blowhey. I see. I see. Wait, is that real? Anyway, I have the blowkey now.
I wanted the most was called the blowhay or the block. Trust me, I'm Danish. I know the back, or as it's I wanted the most was the blahaj, or as it's actually called, the blowhay or the
blowhay. Okay, yeah, that's how you pronounce it. Anyway, I have that now, randomly. Yeah, my friend went to an IKEA a few weeks ago, so I asked him to buy it for me. For no reason in particular. So yeah. Yep, the blowkey. Yep. So, back to this one. This question, obviously we need to find a mu we need to find a value of mu such that mu y primed plus mu y cos x is equal to sine of 2x. So we need to find some value of mu that would turn this whole thing into mu y prime. Obviously, I stopped writing the parentheses, but you get the idea that mu here must be a function of x. And we do know from the formula that the function of x that that function of x has to be mu from the formula that we just got earlier. We can prove it. We can reprove it again, but if you didn't catch it, but the formula for the integration thing is going to be this. This is according to our derivation earlier. Again, this time p of x is cosine. It's a cosine function. And so we multiply by mu, and then we have to force mu such that we have to force that mu has to be some value, specifically this, so that once you take the derivative, it becomes once you plug it in, you can combine these two terms into the derivative, into the derivative of one function. I hope I don't choke on water, because I'm laying down right now. So normally, when you integrate it, you're gonna end up with something like integrating cosine. You get a sine function. Of course, you're gonna get a constant after it. So this constant can be written as, this according to the rule of exponentiation is gonna be e to the power of c, which is just gonna be e to the power of k. No, which is just gonna be k sine x, but it doesn't matter. The k here doesn't matter. We can cut it out. We can cancel it out because because if you plug mu back in here, all the k, I forgot to write the mu over here. Because if you plug it in, if you plug k e to the sine x up here, all of the terms will have k in it. So we can kind of cancel them out without affecting the rest of the calculation. So I'm just gonna cancel that guy out. Which means now we're gonna end up with e to the power of sine x times y primed plus e to the power of sine x times cosine x times y, and it must be equal to e to the sine x times sine 2x. And Jesus Christ, that looks a little scary, because what we're gonna have to do is we're gonna have to integrate the right hand side later on. Which I'm a little scared, because how would I do this? Well, that's a future problem. Whatever. This right hand side, you can prove it. It can be proven that it will be equal to e to the sine x. Nope, not sine y. E to the sine x times y prime times y. If you use the product rule, you're gonna get the one on top. On the right hand side is just the same thing. E to the sine x sine 2x. I'm pretty sure I copied the question, right? I copied the question correctly. How the fuck do I do this? I see. Okay, I got it. Okay, actually, yeah, that actually is kind of clutch. Okay, so I'm gonna integrate both sides. Obviously, the left-hand side is just gonna become e to the sine x times y, and the right-hand side is gonna be the integration, the integral of e to the sine x. Sine 2x here is an identity that you should remember. It pops up quite often. Sine 2x is gonna be equal to, hold on. Sine 2x equals to, can someone in chat answer? I'll give you time to type. 5, 4, 3, 2, 1.5, 1.25, 1, 0.5. I don't fucking know. Whatever. It's just equal to 2 sine theta cosine theta. In this case, so in our case it would just be 2 times sine x times cos x dx, which comes in kind of clutch because cos x here dx here is going to be, both of these can be combined into just d sine x. This technique is known as u substitution. You basically letting u equals to sine x, we get that du by dx equals to du by dx equals to cos x, which means that du is equal to cos x dx. So du here is just u equals to sine x, so we plug that in, we get d sine theta. So we now have sine theta, sine x over here. We have we have 2 times integral of e to the power of sine x, and now we have, and on the left hand side we also have the same thing. For the sake of simplicity, yep, that's u. That technique is u substitution. For sake of simplicity, what I'm gonna do is I'm gonna just write this down as e to the u, and this thing is just gonna be u e to the u times the u, which is equal to u times d e to the u. We use the same strat, right? So if we let d e to u divided by u equals to e to the power of u, this is like by definition. No, not by definition, but like, you get the idea. Like, this is a common knowledge. This becomes e to u, d e to the u equals to e to u du, which means that this whole expression, which shows up over here. No, not there. Hold on. Which shows up over here, can be changed into d e to the u. Yep. More u substitution. Kind of. This is actually a strategy called the integration by parts. I won't go into it, but what we're gonna get is we're gonna get u e to the u subtracted by integrate of u e to u du. This technique is known as integration by parts. So like, integration by part basically tells you that if you integrate f dg, you can change it into, you can swap the orders. That is, you can integrate g with respect to f instead, like this. But you're also gonna have to add in this little guy over here. Yep. So we're gonna have the integration by parts, and obviously there's gonna be a constant term over here. So the integration on the right is simple. It's just gonna be e to the u subtracted by, that's just gonna be the same thing, e to the u. So we multiply that by 2 because I distribute 2 over in here and over in here. We have plus c, we have e to the u over here, and we have y. So that means the answer is, I'm getting cramped, but I don't want to like open a new page just to write like 2 more lines. I should have used up more space over here. What we're gonna end up with is what we end up with is y is gonna be equal to 2u minus 2 plus c over e to the u, which means therefore y is going to be equal to u plus, no, it's 2u plus 2 minus 2, 2u minus 2 plus c times e to the negative u, which is going to be equal to 2 sine x minus 2 plus c e to negative sine x. And this is the value of y. And that's our answer. This answer is probably correct. I'm not gonna like. Yeah, you can check it yourself. I'm confident that I'm good enough to do math competently to the point that I don't need to check. I'll check it after the stream. Alright. This stream's a little less talkative than the previous ones. So let's talk about something cool. Yeah, it's probably correct. I hope it is. Let's talk about something cool while I copy paste the next question. So, how have you guys been? I haven't streamed in like a few days, so like, yeah, might have affected it somehow. Also, I just realized they used the that's weird, because I realized that this homework uses Microsoft Word for. Yeah, the professor used Microsoft Word to make this question, not LaTeX. No, I like that. You've been good? You've been good. Great. That's great. The stream delays quite a bit. But like, it's the best I got right now, sorry. Yeah, I just noticed. This uses Microsoft Word. But like the previous homework set, they used, I'm pretty sure it's like, yeah, they used LaTeX for the previous set. I'm pretty sure. Yeah, the professor used LaTeX for the previous set, but like not this time. Okay, so here we have the hint to solve for x in terms of y. So you know what? I'm gonna trust the hint. Microsoft Word. Do you guys know LaTeX? You guys should learn LaTeX. It's a cool thing. How do you write it? I think it's LaTeX. Like this. I think it's written like this. LaTeX here is basically you program something. It's like HTML, in a way that you program something, and it outputs some very neat You also have like cool as fuck equations. Yeah, it's a funny math coding language. So like LaTeX is really cool. You guys should learn it. I have a LaTeX bot in like pretty much every server that I can. I put it in as many servers as I can. So that's that. Alright. So, solving for x in terms of y. What can we do? How do we do that, in fact? How do we solve for x in terms of y? Because right now, we solve for y in terms of x. So, the thing that gets copied if you copy from Desmos. Yes, yeah, I'm pretty sure Desmos uses LaTeX for rendering. Let me try. Let me try and write 2/3 and copy from Desmos. And then let me try and type it in here. Yeah, it is LaTeX. Desmos uses LaTeX for rendering. Yeah. It's really cool. Alright. So, right now we have to solve for x in terms of y instead of solving for y in terms of x. But here, we are taking the derivative of y with respect to x instead of x with respect to y. So how do we... voice crack. So how do we change that? Well, there's this neat little thing called a reciprocal property, or whatever it's called. But it's basically that 1 over dx, dy by dx is equal to dx by dy. So, from this we can now find x as a function of y, which is what the question hinted us to do. So we're gonna do exactly that. So from this whole equation, I'm gonna take the reciprocal of the entire equation, so that we would have 1 over dy by dx is equal to 1 over 3y over 3 2 over 3 minus x. So that would be the cube root of y squared subtracted by x. I think. Yeah. And so from here we can use the reciprocal thing to get dx by dy equals to 3 cube root of y squared minus x divided by 3y, and so we have this. And with this, we're supposed to be able to find x in terms of y. Alright, how do we do that? Well, first of all, I'm gonna move this term up a little bit. So that we would have 3y dx is equal to 3 cube root of y squared subtracted by x, all this times dy. Should I do something else? Oh, wait, never mind. I think I got it. Yeah, I got it. So what we do here is we solve it by bringing this whole thing to the other side. So we would have 3y x prime. X prime here means dx by dy, by the way. It's gonna be equal to, no, and then I bring negative x to this side, so it becomes positive x. And it must be equal to 3 cube root of y squared. Yeah, 3 times cube root of y squared. And this is almost the exact same form as the other one. This one that we did. It's just that right now, the thing that's in front, right now, we just swapped y with x, and you get the idea. But the p here, instead of being in front of the x, it's in front of the x prime, which is not what we want. We want it to be in front of the normal x over here. So we just divide the whole thing by 3y. By dividing the whole thing by 3y, we're gonna end up with x prime plus 1 over 3y times x must be equal to, what is that? 3 and 3 cancels out, so we're gonna end up with cube root of 3y squared divided by y, which is gonna be equal to cube root of y, 1 over the cube root of y, yeah. I think. Yeah, that's probably it. So now we have the exact same equation. Not exactly the same, but like you get the idea. It's the same general shape of the equation. It's in the same form. Yep. It's in the same form. We can use this strategy. Again, we can use this strategy by finding the integration factor. Multiply both sides by mu, which is going to be a function of y now. This thing is 3yx equal to 1 over cube root of y. Actually, this is going to be mu over cube root of y. With the fact that mu is going to be equal to e to the power of integral. If someone doesn't know where this comes from, it'll make sense once I get it. P here is going to be what? P here is 3 over 1 over 3y, so this is going to become e to the power of 1/3 natural log of y, which is going to be equal to what? Which is equal to y to the power of 1/3. Yeah. So we multiply that in. We're going to end up with mu x prime, which is going to be y to the power of, which is going to be cube root of y. Boop. X prime. This one we're going to end up with what? Cube root of y divided by that guy is going to be 1 over 3 cube root of y squared. Yeah. And then x. And then we have mu over here, which is going to become 1. Right hand side becomes just 1, which is simpler. Much simpler. Now what? Now we solved it. Almost. We do know that this one is going to end up being what? This whole expression, you can prove this yourself. Again, you should do it. You do it. The proof is left as an exercise for the reader or the watcher. In this case, we're gonna end up with d by dy of the cube root of y times x is equal to 1, which means that the cube root of y times x is going to be equal to y plus some constant. Over here we integrate both sides by the x. So now we have x is going to be equal to cube root of y squared plus c times the cube root of y to the negative 1. And that is our answer. We got x in terms of y. I don't think we need to put it in terms of x. I don't think we need to put y in terms of x, but if we do, we just, we just plug the equation in and find the inverse. I don't know how I would find the inverse of this one, though. But yeah, this is our third equation done. This is our third problem done. So yeah, cool. Any shares? Alright. Now on to the next one. Shares? He doesn't know. What am I missing? Chat, what am I missing? Alright. And then we crop this. And then we paste this in here. Paste. I'm a little sleepy today. I don't know why. Probably because of the long weekend. I fucked up my sleep schedule for the long weekend, making music and shit, and also my video. All right, so now we have this. This equation is a little different now. Yeah, this equation is going to be a little different because this equation is another form of exact differential equation. When it comes to this kind of equation, what we do is we assume that there exists some function, right? Assume there exists a function phi that is a function of both x and y. So the differential of this function, the total differential of this function, is equal to that function is equal to the partial derivative of that function with respect to x times the infinitesimal change in dx. And then you add that thing with infinitesimal change in dy, and we have this. And now we hope that this whole thing becomes 0. That makes sense? If this thing equals to 0, oh, I made it. Welcome to the stream. Item review. Partial derivatives. Yep, we are getting into the partial derivatives territory now. Actually, no, this doesn't necessarily have to be 0, but in our case, what we want to do is we want to assume. What we want to do is we want to let this guy be 3x squared minus 2xy plus 2. And the partial derivative of phi with respect to y should be equal to 6y squared minus x squared plus 3. Or whatever you call it. Yeah, this is partial derivatives. Indeed, you call it like that. Yeah. Let those values be that. So that if this is true, which we haven't checked yet, but we will check it in a bit. But if this is true, then the equation up here, hold on. If that is true, then the equation up here, not the equation, then the expression up here, this whole thing up here, if this guy is equal to this guy is equal to this guy, then we can write the equation above. Then we can write it as d phi equals 0. Because this left hand side again is equal to d phi. If this whole thing is indeed equal to this one, and if this whole thing is indeed equal to this one, then we can write this as d phi equals 0, which means phi is a constant. Yeah, because its total derivative is 0, which means if you change x, I'm having a mix of mashed potato with hot sauce for dinner. Nice. That sounds delicious. Yeah, mashed potatoes. Potatoes are nice. Yeah, really nice. Meaning that this whole thing is a constant. That means if x increases, then y must decrease in the same. Then if this term is positive, this term must be negative in some way. They have to cancel each other out. Yeah. Ultimately, it means be linked together somehow, and that link together is from the from this function, from this phi being a constant. So let's do that. First, we have to verify. First, we're going to have to verify that derivative of this is equal to 3x squared minus 2xy plus y. And this one equals to 6y squared minus y squared plus 3. We have to prove that these two are partial derivatives of the same function. Which we can prove that, because if partial derivative, okay, so here's a fact about partial derivative. If you take the second derivative with respect to x and y, it's going to be equal to taking the derivative with respect to y and x. What I'm saying is the order of the partial derivatives do not matter. Which means that if we take the derivative of this thing with respect to y and take the derivative of this thing with respect to x, the result must be equal. Makes sense, right? Yeah, if we take this derivative with respect to y, we are gonna get derivative of phi with respect to x with respect to y. Over here, if we take this guy with respect to, if we take this derivative with respect to x, this guy's gonna be phi, derivative of phi with respect to x with respect to y. Yeah, makes sense? Good, okay. So now we prove that by taking the derivative of this guy with respect to y. Which is going to turn out to be equal to negative 2y. On the other hand, this term, this expression is going to become, take the derivative of this with respect to x. Partial derivative with respect to x, we're going to get this thing. Taking the derivative, we get, that is not, that is supposed to be x, sorry. Taking the derivative of this, we get negative 2x, which means both of these two values are equal. Therefore, this is indeed a derivative, this is indeed the partial derivative of x, of phi with respect to x. And this is a partial derivative of phi with respect to y for some value of phi. So now what we have to do is find that value of phi. Okay. Okay, let's see. Let's see how we can do that. We have phi here. Derivative with respect to x is equal to 3x squared minus 2xy plus 2. So, to find the value of phi, we're gonna end up with, we're gonna have to integrate this side by x. Okay, but here's the neat. Can't wait for college. Yeah, university is really nice because you finally get to learn what you really want to learn. Integrate that, we get x too. Because like school is kind of boring, not gonna lie. School is boring because like you just learn irrelevant stuff most of the time. It does incentivize you to like learn and shit, but like no, this is not y, this is x, this plus 2x. It incentivizes you to learn for some people, but like most of the time it doesn't. Anyway, this is gonna be the value of phi, but not the complete value of phi. You see, in this constant here, it has two parts. We have the part that is constant with, that is absolutely constant. That is, it's a function. It's a fucking constant. Yeah. The 5 subjects I have no interest in that have to take at school. I know, right? They're so boring. So yeah, this constant here is constant in x. This means this value could actually vary with y. This function c could vary with y as well, which means that this whole thing is not complete just yet. let me show you what I mean. We integrated this with respect to x. Now it's time to do the same for y with respect to y. So derivative of phi with respect to y, we end up with 6y squared, right? Minus x squared. Minus x squared plus 3. If we integrate that, we're gonna end up with we integrate that with respect to y, so we're gonna end up with this is y, so this is gonna be 2y cubed subtracted by x squared y plus 3y, and then of course we have another constant from the integration, which may be constant, which is constant with respect to y, but it might not be constant with respect to x. So as you can see here, these two are completely different. Well, not entirely different, but you can see that there are terms that shows up over here, like like over here on the left hand side we have this term and this term that is absent in this on this side. On the other hand, this side we have these two terms that do not appear on these sides. Well, I lied. It does appear because because this term is in this c right here. It's in this constant of integration right here. Similarly, I can't say, yeah. It's similarly, these two terms are present in this form in the c function over here as well. So overall, the value of phi or phi, I don't know how to pronounce. I still don't know how to pronounce it. And so overall, the value of phi is gonna be equal to every term on both every term in both equations. So every term in both equations, we're gonna have x cubed plus 2x plus 2y cubed plus 3y. And then this term is present in both, because obviously it would be. It has both x and y in it. And we're going to have some constant that we don't know. That is absolutely constant. This one is not it's not in terms of x or in terms of y anymore. This is just totally a constant now. Pretty sure it's pronounced phi, but I don't know. Yeah. Screw it. I'll figure it out later on. Whatever. Alright, and we've been streaming for approximately 1 hour now. 1 hour and 2 minutes. No, like pi, but phi. Oh, yeah. Could be. I've seen both. I've actually heard both pronunciations. Phi pronunciation. Pronunciation. Let's see. What does Google tell? How to pronounce phi or phi, whatever. Let's see.
We are looking at how to pronounce.
What the fuck? Okay, thank you. You know what? I'm gonna ask my Greek friend. Be right back. Not like that. I pronounce phi anyway because it's cleaner on the tongue. It is, yeah. Let me ping him real quick. How do you pronounce? Fun fact: I installed the Greek language in the Greek letter in my keyboard because I want to write equations more cleanly when I don't have LaTeX available. All right, back to this. Now, while I wait for his answer, I'm just gonna we can proceed. All right, so that was such a deep voice from that guy. Yeah, I got jump scared by the YouTube as well. Yeah. All right, moving on. So that means this value is a constant, according to this one over here. Because we wrote this whole thing can now be written as Okay, let me try to write it. So this means that the differential of x cubed plus 2x plus 2y cubed plus 3y minus x squared y plus c must be equal to 0. This is what we got from earlier. This must be equal to 0, which means that this guy must be a constant. Plus 2y cubed plus 3y minus x squared y equals to some constant. And of course the c inside here is going to be subtracted. I can move it over here. It's going to be constant subtracted by c, which is still a constant. So I'm going to remove it. So the value of c doesn't really matter. Which means we now have the relation between x and y, and I think that's just it. I don't think we do anything else here. Do we? Should I try to factor out y? And nah. I think we're fine as we are. So yeah, this is the relation between x and y, which means that this whole thing must be constant, and I'm gonna copy paste that and put it in decimals.com because I wanna show you guys how it looks. I don't know how it looks either, but I want to show you guys at the same time. Let's see. Let me check. 2y cubed plus 3y minus x squared y equals to constant phi. Okay. And now if I share my screen, it's probably black screen right now. Yeah. Where's my Opera GX? I can't share my Opera GX. Give me a sec. Okay, decimals.com. I summoned the. Where did it go? Why is it not working? Come on. That's not the right thing. Where is my? Wow, such screen. Yes, I know, right? It's not even. Okay. Yeah, the screen is black. The screen is back. Just admire the equation while I trying to get this to work. Why is it just not working? Is it like, are you here? Please, OBS? Streamlabs, please? Please detect my window. Thank you. Please, is it working? It's not working. Okay, no decimals for you guys today. This is so sad. Oh well. You know what? I'm gonna give it another try. Maybe it's because I have multiple Opera GX open. Maybe it's because I don't know. I honestly don't know. I'm just. Yeah, no, it's not appearing. Give me a sec. I could make a new source. Give me a sec. New source. How do I add a new source? There we go. That's how I add a new source. Window capture. Add that source. Window capture. Add a new source. Thank you. And we add the Opera GX. There we go. There we go. There we go. Okay. Yeah, let me scale it down a little. There we go. All right. So this is the equation for x and y. If phi equals to 1. So obviously if we scale it around, the equation would be different. And yep, yay, decimals. And yeah, the equation is going to be different. All of these will be different depending on the value of phi. So obviously the answer here is going to be you're going to have multiple answers, infinitely many answers. But so when you solve a first order differential equation, you will always get an infinite number of answer. One sec. Okay. You will always get one. You'll get infinitely many answers, but you will get. But by that infinite, it means you have one free variable. You can set it to be anything. In our case, it is phi. Phi is our free variable. But if you have second order differential equation, we're gonna have multiple sliders that we can slide around with. So in that case, that's gonna be like we're gonna have multiple values that we have to. Yeah. Evil constant that can be literally any number. Literally, yep. I don't think anything forbids it from some equations. They might as well even be complex numbers or imaginary. I closed my other Opera GX tabs, which means I don't have my my homework tab ready. Okay, let's see. But I did send the question problem some time ago. Let me find it. There we go. Found it. All right, and that's my differential equation homework completed. Oh boy. Here we go. I just realized this is homework assignment from 2021. Like, my professor has been reusing it for 4 years. That's insane. Alright, width is 21, 29.7. I'm gonna grab, like, each individual thing. Oh no, we have to submit it by August 2021. We already passed the due date. What do I do? Okay. Oh no, I've been procrastinating on this homework for 4 years. Whatever will I do? Okay, let me just copy that and paste that here. Keep canvas size. And we shrink this down. So, first question, kinda simple, pretty simple. It's just Newton's law. Good job, professor. How's he today? Or she? Actually, I don't know. I think he has he's hosting an event. He's hosting a booth in a science fair event right now. Actually, maybe not right now. It's actually kind of late. But I think the event has been going for like 2 weeks. So, or maybe one. I'm not quite sure. But it's a science fair event, I think. And I honestly wanted to go there, but I never had the opportunity to. I don't think I'll get to go there this year. Maybe next year. There are a lot of science fairs that are being hosted regularly, so I don't really mind. But I think he's doing fine. He's probably a little tired though. So, a simple pendulum consisting of mass m at the end of a massless rope of length L swings in a vertical plane with the initial angle theta naught. Measured from the vertical line is released from rest. Okay, this one is classic pendulum setup. Absolutely classic. What we have is dashed line over here. We have dashed lines over here. We have M. Actually, wait, hold on. Let me check my CPU real quick. My CPU, is it okay? Wow, Streamlabs is actually using up less CPU than I thought. Never mind, it's back up. It's going back up. Alright. So obviously here we have a simple pendulum, a silly little pendulum. The force that's pulling it down, the acceleration that's pulling it down is g, which means if this angle is theta naught, well, theta for general angle theta, it means that this one is also theta. You know how, yeah, that's just parallel line angles. This one's also theta naught, which means that the acceleration along the radial axis away from the pivot point, the acceleration in the radial axis here is going to be g cos theta naught, whereas the acceleration tangential to the radial axis is going to be negative g sine theta. Okay, negative g sine theta. So the acceleration here is going to be theta double dot times L. L is the length of the pendulum. Hold on. It's going to be theta double dot times L. This is the acceleration because theta dot here is how far the theta dot here is, a theta double dot is the acceleration along this theta thing, along this angle. And obviously the distance from here to here is proportional to the angle. So the acceleration is also going to be proportional to the angular acceleration. Does that make sense? Yeah. The acceleration, this is like by definition, the acceleration along this axis is going to be equal to negative g sine theta. This is not supposed to be theta naught. What is? What am I saying? These aren't supposed to be theta naught. Okay. There we go. All right. So that's so this is our equation of motion. Yeah, this is exactly what we needed. Yeah, this is the answer to the first question, which is easy for now. Well, not really easy, because this differential equation is not solvable. You can't solve this equation. Give me a sec. G over L sine theta. You can't solve this equation analytically. Yeah, there's no final function that would be normal, I suppose. So what you would end up having to do is you would either have something like a series expansion to make this, or you would have to calculate it numerically, which is what people tend to do. Which, in fact, I should do it on Desmos. Give me a sec. Have I done it before? I don't think I have. You know what? I'll do it in a bit after I might as well do it now. Hold on. Alright, Desmos.com time. So first of all, I'm gonna make a pendulum. So I'm gonna make this point equals to I'm gonna first call L equal to 1 for the length of the pendulum. And so the point of the pendulum should be cosine of variable theta. I'm gonna call V theta here for a variable named theta. And this is gonna be cosine, and this is gonna be sine of V theta. And that theta should be anything, yeah. And then I make this negative so that it would be, that is not, I did it wrong. It's supposed to be sine here and then cos here, so that it would be like that. Yeah, okay. I could make this negative sign for the sake of, I don't fucking know. Yeah. So now we kind of have like this little pendulum thing that we can kind of make. For the sake of visualization, I'm gonna make the point like much bigger. Did that point outline. How do I make the point bigger? I swear. Oh yeah, there we go. There we go. 8? Is 8 big? Nope. 10. I'm gonna make it like 20 or 25. How about that? Yeah, good enough. And then I'm gonna add a polygon. I'm gonna add a polygon for between the point 0, 0 to our pendulum right there. And this is gonna be our pendulum visual. And I'm gonna put all that into the gonna put all that into this folder. Okay, so now we can control the value of theta. Obviously here we don't okay, yeah. Obviously here we don't have anything that would make it fall around just yet. I should log into my account, yeah. Because with my account I can use the ticker feature. Okay. So now L, I'm gonna keep it at that. So I'm gonna keep the pendulum that, and then I'm gonna make the G equals to 1. No, you know what? 9.5. I'll set G to 9.5. So now we know that this is the value of theta. So we're gonna have the velocity of theta, which is gonna be theta dot. I'm gonna call it the theta dot, and this is gonna be 0. And so now we should have some actions. I'm gonna make a folder named actions, and this action is gonna be updating v theta depending on the value of the time steps. So I'm gonna make, oh shit, okay, I thought I deleted it. I'm gonna call this v of dt. It's gonna be the small time step for each action, and I'm gonna call it like 0.1. I should also name a folder variable. Variables. This is for a simulation, and so the first action I'm gonna call A1. It's gonna be updating v theta. V theta here is the variable named theta. Should be updated by adding the theta dot. And then multiplied by dt. Yeah. And so if we run A1 every tick, we're gonna oh right, v theta. If we run that, we're gonna have a quote-unquote pendulum that is currently unaffected by gravity. So yeah, that's Desmos right there. Okay, cool. So that's how it looks right now. Next up, we're gonna have to implement gravity. In our case, theta double dot. Theta double dot is the acceleration of the angle theta. In our case, we have already discussed the value of theta double dot in the paint.net, right? In the paint.net, we have discussed that theta double dot is equal to negative g over L sine theta. So pulling Desmos back up here, we have negative g over L sine of variable theta, sine of the current angle theta. Which means we now have another action to keep track of. That is v theta dot, which is the velocity in theta. It's going to be equal to v theta dot, which is just itself, and then added by the acceleration times the time step, the small time step. And now if you run this, what we're going to end up with is a pendulum that goes very quickly because I set the value of g way too high. If the value of g is way too high, right? That kind of happens. Momentum will no longer be conserved because of floating point errors. Yeah, third stream. Yep, welcome to the third stream. Okay. Also, the smaller the time step, obviously, the more finer the pendulum becomes. Right now, I'm gonna run it. There's gonna be nothing because that's where it starts. If we start it at say over here and I run it, we're gonna see a pendulum that's swinging round and round. I'm having a hard time catching up and understanding. That's fair. I'm just simulating a pendulum on Desmos.com right now. And as you can see, it is doing fairly well. The problem is that eventually it will go a little out of control. Let me explain what I mean. By going out of control, it means that, let me calculate the energy. E is going to be equal to the total energy is going to be negative G is going to be mass times the height, which is going to be cosine of theta. This is the potential energy. MGL cos theta. This is the potential energy. And then the kinetic energy is mv theta dot. This v here it doesn't mean velocity. This v here means variable. This is the variable that represents the angular velocity. So mv here, I'm streaming it, right? Okay, I'm showing the screen. Okay. So the velocity here, so the actual linear velocity is going to be theta dot multiplied by L squared. And this is the actual value of, this is the value of the energy, which we can, which I'm going to set mass to be equal to 1 for the sake of simplicity. And you can see that the energy starts off with, I should reset. Hold on. I'm going to reset this to 0. And I'm going to set this to something like that one. Okay. So, according to our motion, according to our equation of motion, from this, energy should be conserved. It should be conserved, but the problem is that the simulation makes it a little hard to be conserved. If you can see, you should probably see that the energy will be changing a little bit. By a very small amount. Okay, that's not very small, but the energy will be changing. This is because of the rounding errors done because of the computer. And not just the rounding errors, it's just that the computer kind of struggles to keep up with all the... because we are using discrete time steps as well, yeah. Discrete time steps makes the simulation a little weird. As you can see, I think we started from here, but now it's going up further than where we started. So there's like a small flaw that we can't really fix in Desmos. I'm pretty sure there are ways to like prevent this kind of stuff, this kind of error from running simulations, so that you'll be able to run the simulation for much longer. But yeah, this is our pendulum simulation. Actually, let's check out what I have for in my graph. What do I have over here? I do have this. Don't mind that. I do have this one. That's a quantum mechanics simulation. Basically, please reset. Yeah. This is a quantum mechanics simulation. This thing is the imaginary part. This what is that? This is the wave function. Not really wave function. Hold on. This purple part is the probability of a particle being over here. And then these two are the wave functions that represents this that represents the state of a particle. So obviously over here the wave function is higher, so there's a higher probability. I should normalize the x-axis. I should normalize the y-axis. What am I saying? Negative 10. Yeah, I should. Yeah. All right. So this is gonna be the value. So here, as you can see, we have the real part and the imaginary part because the wave function is complex. And if you square them and add them up together, you're going to end up with this probability distribution function. If I run the time, you can see that the particle is moving to the right. Yeah, and as the particle moves further to the right, it gets more spread out because the momentum is kind of uncertain. So it could have been like a little slow and it probably just ended up here, or it could have been very fast and ended up over here. So there's the what is it? Function that we have the uncertainty in the momentum and the position, and that's the traveling wavelet thing. I also made this Perlin noise generator thing I did. It's quite resource intensive though. I'm not quite sure if my computer can run it while streaming. I don't think it's gonna render within today, so I'm not showing that. But you can see from the preview as the Perlin noise. I also fucked around with the Bezier curve. Yeah, it's just it's just a Bezier curve. You can add in as many points as you would like. You can add in an infinite number of points. This is generalized. This Bezier curve has a formula that I use. These three are actually like, I use different linear interpolation functions. What am I saying? I should be doing homework. We should be doing homework. What the fuck are we doing? Okay. Alright, back to our homework, because that was part 1 done, and that's not even the hardest part. Okay, I'm gonna close the decimal screen. There we go. Okay. That was part 1 done. And we then ran the simulation. Now, this is a difficult question. And then after this, it's just gonna be a little mathematics trick. I haven't figured it out myself yet, but we'll figure it out together. We still have space, so I'm going to put it here. Show that the period t is given to be this, where g is the magnitude of the gravitational acceleration. So it's just the same thing over here. This one is quite difficult. Admittedly, it took quite a long time to do this one. It is a little difficult. So let's see. As I said, this function, you can't solve it analytically. You can't solve the actual value. You have to numerically compute, as we did earlier. You have to numerically compute the pendulum. So how do we find the period if we don't know the function itself? How do we know when the period will when the function will come back to where it was? Well, we use conservation of energy over here. This question is honestly very hard. And by very hard I mean like compared to the other ones over here. I think this is deserving of like I think this is some TPHO level, TPHO Thailand Physics Olympiad, because I've seen stuff like this before in TPHO. Something that looks similar to this. Because, like, I competed in the TPHO, Thailand Physics Olympiad, and I got a gold medal somehow. Imposter syndrome. I have imposter syndrome. I somehow got gold medal, but yeah, it's basically the Olympiad for nerds. But, and I swear, this kind of question, you would see it in the national rounds, I'm pretty sure. So yeah. This is, that is how difficult this would be. So imagine how excited I was when I figured out last night. No, not last night. 2 nights ago. I was like laying in bed. I was like ready to go to sleep, and I was like, how do I do this problem? Because this question, I wasn't given this homework like today. I couldn't do this problem, so I didn't stream it. I want to make sure that I could. I wouldn't waste your time. Although I kind of am right now. But you get the idea. This one is a little hard, but I figured it out. Here's how we do it. Click off the stream if you want to like do it yourself first, but here we go. What we do is we use conservation of energy. Over here, right? We have the object's mass. I'm not gonna care about mass just yet. Okay, so the energy here would the potential energy at this point at an arbitrary angular at an arbitrary angle theta. You know what? I'll set this one be theta naught, and then this one be an arbitrary, and this one be theta. I'll draw that out later. Let me just. Okay, so this we released it from the initial angle theta naught. What does this mean? This means that initially the energy in the system, the initial angle of the wait, hold the fuck up. What? Where did I go? Hello? Oh, okay. Yeah, sorry. I accidentally closed the PNG tuber tab. Sorry. Okay, so the initial energy must be negative mg L cos theta naught. I set it so that over here potential energy U equals 0. No, actually, yeah, I'm just gonna call the point up here h equals 0. So down here h is gonna be negative. How much negative? Well, this length is L. This angle is theta naught. So therefore, this height over here is gonna be L cos theta naught. And therefore, the initial energy must be negative mgl cos theta naught. Alright. What happens to me? Okay. Now, if I'm on a different layer. Give me a second. Now, if I redraw that, but for an arbitrary angle theta, what do we get? If I redraw that with an arbitrary angle theta, it means that the velocity is no longer going to start off at 0, right? The velocity is going to no longer start off as 0 because now it has some velocity attached to it. I'm going to call this V. And then this theta is going to be any theta. It doesn't have to be the initial theta. So this can be any theta. Obviously, in the same sense, over here the length must be L cos theta. L cos theta. And therefore, the E at any point, the energy at any point, must be equal to the kinetic energy, 1/2 mv squared, plus the what is it? Plus the potential energy. In this case, it's going to be plus mgh and g plus mgh, which is going to be mgl cos theta. This is our conservation of energy. So it means that v, the velocity at any point theta, must be equal to We'll solve that one later. Let me just set up the conservation of energy equation real quick. We have negative mgl cos theta naught is equal to 1/2 mv squared minus mgl cos theta, where we can cancel out the m's. So now we're gonna have, so now we will have v at any point theta. After you release it, the velocity at the size of the velocity at any point theta must be equal to. Give me a sec. 2 GL times cos theta minus cos phi. No, not phi. Theta naught. Why am I talking about phi? Oh yeah, has he answered me about the phi yet? Has he answered me how to pronounce phi? Yeah, it's pronounced phi, I think. Wait, is it phi or phi? He said fi. Is that does fi mean phi or phi? I think it means phi. But like stuff like, you know, but the word ski, you pronounce it ski, as opposed to like stuff like but high, you pronounce it as high. But ski, you use e. It's pronounced like ski. But here you have pronounce it like high. So like it doesn't make sense. Why does the same thing pronounced differently? Okay. Anyway. So this is the velocity at any point theta. So that means the time it's gonna take to get from theta naught, to traverse an angle of theta. Okay, let's say we are over here. I'm gonna not draw the pendulum. I'm not gonna draw the bulb, so it would be easier to see. But when you move up here, right? I drew that too. Okay, if you drew it out like this, yeah, circular enough. If you draw it out like this, let's say you have to move from starting point theta. You have to move from the starting point of angle theta, and you have to move up by d theta. Oh no, why would this fine pie get burned? Sorry. Okay, so if you want to move from point here over, if we want the pendulum to move from over here to over here, the distance over here, the distance is going to be L d theta, right? Because this is part of the circle, and you know, you can, if theta is in radian, if d theta is in radians, then the length over here is going to be exactly equal. It's going to be equal to the radius times the angle covering it. So this length over here is L d theta. So the time it takes the time it takes I'm gonna call the time it's gonna take, I'm gonna call d dt. The time to move from theta to theta plus d theta is, I'm gonna call dt. This is the time it takes to move from here to here. Assuming that, yeah, assuming the pendulum falls from here up all the way up here. The velocity is going to be going up this way, so the time it's going to take to move from there to there is going to be distance over the speed, right? Which is L, okay, which is delta S over delta V. You remember that, right? Delta S over delta T V. There isn't supposed to be a delta over here. Sorry. Which is that? Yeah. It's dt. So, therefore, we can set up the equation. dt is equal to, give me a sec, L d theta. Delta S here is the distance, so from here to here is L d theta, divided by the speed at this point. The speed at this point, what is it? Well, we just found it. It's V is square root of 2gl times that guy. And this is our dt. This is our small amount of time to move from here to here. And if we want to add them all up, we integrate it. Yeah, I'm just going to integrate it. If we add them all up, we're going to have integrating from 0 to some big T over 4 over here. I'll explain that one later. Just give me a moment. This is going to be equal to integrating from 0, starting from over here, all the way to the point where you get to a point that is theta naught. So I'm going to put it here. And so we end up with this equation. L over square root of 2gl cos theta minus cos theta naught and d theta. Now, why is this t over 4? Well, because of symmetry. If you want to find a period, we know that the time takes from up here to swing down here should be equal to the time it takes to swing from down here back up to the other side. And so overall, the time it's going to take to go from here down over to here and then back up here is going to be equal to 4 times the time it takes to get from here up to here once. Yep, symmetry. I was going to use that word. Thank you. Symmetry. So that means this is t over 4, which is the period. The time it takes for this ball to go up and then back, up, down, yeah, is the time period. Therefore, we have set up the equation that t must be equal to 4 times this guy, which I'm gonna format it to the to be right. So it's gonna be square root of 16. I'm gonna put everything in a square root. Gonna pull out all the constants. So this will be 16l squared divided by 2gl, and the rest here integrates from 0 to theta naught, d theta divided by square root of cos theta minus cos phi naught. Cos theta naught. I'm sorry. I'm getting a little sleepy. I should take a nap after this. Cancel these guys out. This one becomes 8. So now we have this whole thing. And to write it more neatly, we're going to end up with the square root of 8L over G times the integral of square root cos theta minus cos theta naught d theta. And this is 0 naught and 0. Which is exactly the same thing that the question gave us. Yay! So we got it. We solved it. Section B. We solved section B. Yay! Cheers. Oh boy. Next up, we're gonna do the next problem. Cheers, cheers indeed. Now the next problem is now we have to let epsilon equals to sine theta naught over 2. Hold on, let me just stretch real quick because that was one hell of a problem. Okay, this one is gonna be, I don't know how to put this. This one's gonna be a little difficult as well, but I haven't done this one. I thought that the other one was probably the most difficult part of the problem. So we should be able to do this, right guys? So we're gonna start off with the equation we got prior. And we're gonna try and substitute the values in. Theta. Is this too big? It is kind of big, so I'm gonna zoom in a little. And then we have d theta divided by, you know, if I could write the division sign, the fraction sign better. Okay, this cos theta subtracted by cos theta naught. Okay. And that equals to that. Now we show that that equals to that. Alright. How do we approach this? Okay, let's just use the identity, straight up. I forgot the identity. Give me a sec. Sine a plus, no, cos a plus cos 2a is equal to that, right? Yeah. So, if sine equals to that one, it means that dimensiometric identity. Yeah, precisely. Let me drink some water. If epsilon equals to that, right? Let's see what we can do. We also have another identity. Cos of 2x must be equal to, it can be equal to a lot of things. Namely, we have what? One minus 2 sine theta. One minus 2 sine squared x. I think that is right. I think that is right. Yeah. I think so. Alright. So, Now with this identity, because we now know that cos of theta naught is going to be equal to 1 minus 2 times sine of theta naught over 2 squared. Alright? And that's already our epsilon. So this one becomes 1 minus 2 epsilon squared. Because epsilon is sine theta over 2. So this becomes 1 minus epsilon squared. Well, now what? Math. Math indeed. I don't think I'm gonna be monetized. I feel like some words aren't allowed to be said. I don't know. It may not be that sensitive. It probably isn't, right? I could probably say math, like, repeatedly. Okay, so we're gonna end up with that. Now what? Now, what do we do now? So this thing is gonna become d theta. I'm just gonna call this. I'm gonna keep this d theta for now. This one becomes square root of 1. No, wait. Cos theta is just cos theta subtracted by this guy, which is going to be subtracted by 1 and then added by 2 epsilon naught. No, 2 epsilon squared, not epsilon naught, sorry. I don't know, you're the teacher. Am I? Come on. I'm not that good at teaching. Alright, now. Now what? Chat, any ideas? I'm getting really sleepy. I should not have streamed on my bed, man. It's like it's like I Pavloved myself into falling asleep. I don't want to fall asleep on stream, bro. Do you guys want to sleep stream? Okay, how do we do this? What the fuck do I do? I do have epsilon. I do have this one. How do we show that? How do we make we have epsilon now, but how do we make it epsilon squared? Oh wait, let me try. Sleep stream, but you do physics while sleeping. Canon. That would be canon. Okay, let me try something. So if it's actually 1 minus epsilon sine phi times 1 plus epsilon sine phi, this would indeed give the same result as this one up here. So we have to find a way to make it look like that. What do you do? Or do we not need to do that? Actually, wait. Can I do that? Is that a thing that I could do? We're integrating. Hold on. We're integrating with respect to. Oh, wait. We're integrating with respect to phi here. But initially, before this, we integrated with respect to theta. Give me a moment. Before this, we integrated with respect to theta, which means, what if, wait. Oh, wait. I think I'm cooking here. So we have this, right? Then we still have this. And then let me delete that real quick. Okay, we still have this. That's still right. Now, I'm not sure if this is gonna work, but I can try. I want to try. Cos theta Give me a moment. Let me just reposition myself. Okay, cos theta, it represents this angle from cos theta represents the angle from here to the static angle theta naught, right? Okay, so integrating from theta here, from theta starting from here all the way to here, is equivalent to integrating this difference over here. I'm gonna call this difference alpha. Alpha equals to theta naught minus theta. So integrating with respect to alpha, integrating with respect to theta, starting from 0, theta equals 0, and then there's something in here, all the way to theta naught, should be approximately equivalent. Should be equivalent, I think. It should be equivalent to integrating something from alpha equals to maximum, which is theta naught, to 0. Right. Right. I think so. Does that work? Wait, would that work? It should, right? You know what? Only one way to know. We gotta try it. So we know that cos theta must be equal to cos of this minus alpha, which is equal to another trigonometric identity, cos theta naught cos alpha subtracted by sine theta naught sine alpha. But here it must be positive because, oh yeah, I think we're getting there. But here this must be positive because this is I think that's the identity, if I remember correctly. Let me check. Cos A plus B. The formula for cos A plus B is, okay, yeah, that is right. Okay. And then what? And then what do we do? I'm actually out of ideas here. Cos theta here is just gonna be 1 minus 2 epsilon squared again, and multiply that by cos alpha, and add that, and then we have sine. Okay. And then add that, we are gonna have sine theta over here. Sine theta naught is equal to 2 sine theta naught over 2 cos theta naught over 2. Is there any other way to do this? Well, I guess not. What do we do now? I'm actually... Yeah, I exam tomorrow. Oh, you have to go? I gotta go. About to prepare for my driving lesson tomorrow. Okay. Yeah. Have a good day. Tessie, have a great exam. Hope both of you have a great exam. I don't have an exam yet, fortunately. But yeah, I hope you guys have fun. Hello, Teo. Welcome to the stream. Uh, how do I do this? Like, how do I transform from this? How do I transform from this to this? I have to find a way to substitute theta. You know what? I'm gonna redo the whole thing. I feel like we've made some progress, but I think I want to do it a different way. You call him Tubo? How else do you call him? I call him Tewo or Tiwo. I'm not sure. Tiwo, yeah. Okay, you know what? Time to redo this. Let's see. So here we have. So here, this is equivalent. This whole thing is equivalent to. I don't have a brush. Okay. This one should be 16 L over G. Integrating that. It should be that, and then you divide it by square root of 2. Literally by definition. Not by definition, by multiplying both up and down by square root of 2, which this one will give the coefficient in front over here. So now all that's left to do is deal with the integral. I forgot the square root sign over here. Which is going to be equal to 4 square root of L over G times the integral of d naught times divided by the square root of cos theta minus cos theta naught. 0 to theta naught. Okay. And now what? Now what do I do? You have to find a way to convert from this. You have to find a way to convert from this expression to this expression. But how? I don't think that works. This is a little difficult. We have to change the bound. We certainly will have to change the bound from 0 to pi over 2. So from here, we have to find something such that the theta naught at the end is equal to pi over 2. But like, what is that thing? You get me? What is that thing gonna be? Damn, this is hard. So like, okay, let epsilon be equal to that. So now we have to show that it becomes this. Should I use the same strategy? I think I could use the same strategy. Cos of 2x. Let me check what formulas I could use. Okay, how about I try that one? Should I... Yeah, how about I try that one? That will become... That's gonna turn into 4 square root of L over G mu. Yup. Hello, Dark God. Welcome to the server. No, not server. What the fuck am I saying? I keep on greeting people like I'm in the Discord server. I'm on a fucking stream. What am I saying? My face when I'm too chronically online. Okay, down here. I'm gonna turn this into not crashing out. Maybe. I don't know. This question might just get me to crash out. Let's see. This one becomes cos squared of theta naught over 2 subtracted by sine squared of theta naught over 2. Right? Right. Which in turn is equal to 4 square root L over G times the integral of 0 theta naught. Down there it's going to be theta. This is going to be square root of 2 cos theta subtracted by 2 times cos theta over 2 plus epsilon times cos theta over 2 minus epsilon. How about that? Does that get us anything meaningful? Doesn't look like it. Then what? Then what do we do? That's actually theta, not theta, not normal theta. Chat, anyone got any ideas how to do this? Okay, let's see. What angle would be equal to pi over 2? What angle would be equal to pi over 2 when theta is equal to theta naught? And it must also be 0 for when theta equals to which angle is it? Pi over 2 is 90 degrees, right? No, that wouldn't work. That wouldn't work. Wait a fucking minute. Wait a fucking minute. Let me try something. Wait. How about I forward engineer? Like, okay. No, reverse engineer. Literally reverse engineer. Let me try. You're the teacher? Oh yeah. I'm the teacher. If I'm the teacher, then we're cooked. I can't do this. If I can't do this shit, we're cooked. Sine phi. Yeah. Sine squared phi. Which is equal to okay. Let's try that. Equals square root of 1 minus sine theta naught over 2 sine phi. And then we multiply that by 1 plus sine theta naught over... Oh! Wait. Sine phi. Wait, no fucking shot. No, I don't think it is. It's not. No, I don't think so. So what if we write this in terms of okay. Let me check the other trigonometric identities. Trig formulas. Oh wow, that is a lot. Let me see. Open image in new tab. Because this one is kind of hard. I'm gonna be real now. This one's kind of hard. I don't know how to go with this. What if I use the product to sum? Bro, I'm stumped, honestly. Okay. I didn't think it would be like this hard, this question. I didn't think so. But here we are, I guess. Here we are. How do I visualize this? Let me visualize it real quick. Because this one is going to be something over the square root of 1 minus epsilon squared sine squared phi. And when you look at that, what I think of is maybe a triangle. Like this triangle, we have like this triangle, right triangle has the length of that, and this one is gonna be, and if this one is epsilon squared sine squared theta phi, this one is gonna be square root of 1 minus epsilon squared sine squared phi. Oh wait. I might cooking. Chat, I may be cooking. So this is actually going to be equal to, let's say we have this angle right here. I'm going to call it alpha. So that means we're integrating. What we're integrating is we're integrating tan. No, not tan. What is it? Sec. We're integrating the second of alpha. Yeah. We're integrating the second of alpha. And then what? And then now we can find a way to turn that phi here is something that we don't know of yet. If I take the derivative, no, the partial derivative, what's it? Sine, yeah. Sine alpha equals to epsilon squared sine squared phi. Which means that cos alpha times d alpha is equal to, now I take the derivative of this with respect to phi. We're gonna end up with epsilon squared sine, this will be 2 sine phi cos phi d phi. which is going to be equal to epsilon squared sine 2 phi d phi. Well, this is cos alpha d alpha. Well, that's not much better. That doesn't look much better. Now what? Now we have that second value. We have to find a way to. We have to find that guy over there, but yeah, this may be the incorrect route. God damn it. Okay, let's see. Let's try that again. How do we get from How do we get from here? Oops. How do we get from here to here? What the fuck is phi? Ah, damn it. What the fuck is phi? Screw it. You know what? I'm gonna do this little approach, like brute forcing approach. Let's see. That one's 1 over square root of 2 cos theta. That one has to be that one's gonna be I'll figure out eventually. Like, come on, there's no way I can't do this. Like, eventually, if I have time, I should be able to get it, I think. Like, it is fairly difficult, but like, I don't think it's impossible for me to solve. I'm quite sure. I got pinged on Discord. Give me a sec. Who dared ping me? Oh, the Wordobot. Okay. So, how do we solve this? This one is 2 sine theta squared. And then this is subtracted by 1 plus 2 sine theta naught over 2 squared, right? Which is gonna be God damn it, my mom is calling me for dinner. I haven't done the stream yet. Wait, I need to finish this. I gotta finish this one on stream, chat. I got it. Come on, I can do it. Fuck dinner. I gotta get this. Okay, so we're gonna end up with I factored it out. We're gonna end up with epsilon squared minus sine squared theta over 2. Wait! Maybe? No, I must be tripping. I don't think so. I don't think that's gonna be it. Gonna write that thing down real quick. D theta. No, that probably isn't it. So we should end up with that form. We have this. but we don't have that. How do we get this whole thing? Okay, what if I use a triangle again? Where I use the triangle trick? Because over here, clearly this could be this would be epsilon squared, and this would be sine, and this one could be sine squared. No, this, okay, this up here is epsilon. Sorry. This up here is epsilon. This down here is sine squared theta over 2. No, this sine theta over 2, not sine squared. And so over here, across here, is going to be square root of epsilon squared minus sine squared theta over 2. And this is going to be our angle alpha now. Let's see if this works. So now what we have is the fact that square root, this whole square root is going to be, so we know that sine alpha is equal to this whole thing. So I'm going to change it to a cosec. Yeah, the cosec of alpha is equal to epsilon over square root of epsilon squared minus sine squared theta over 2. Wait, give me a sec. If theta is 0, okay, wait. What does it mean for theta to be 0 for alpha? It means that these two have the same length. No, if this one goes to 0, it means alpha goes to 90 degrees. But if alpha goes to 90, and on the other hand, if this one approaches, okay, maybe. I think I got it, chat. I think I got it. What if instead of alpha over here, I think I got it. It might require some integration bullshit, but here we go. Here goes nothing. I have like 5 people emotional supporting me. I'm gonna call this thing phi. Therefore, if I rewrite this, if phi, no, okay, wait, let me try real quick. If theta equals 0, this would lead to phi being equal to what? If theta equals 0, phi would be 0 as well. If theta equals to theta naught, then if theta equals to theta naught, then phi equals 90 degrees. Yep, we got it. We found phi. Chat. We found phi. Over 2. Yeah, that is exactly what we needed. We don't. Before this, we struggled to find what phi here is, but now I think I know it. It's a little abstract. I don't know the exact what the angle means, but I think we are on the right path. Well, there are several paths, but I think this is one of the possible correct paths. Okay, so let's see what we can make. Let's see what we can do with this. All right. So we know here. So here we know for a fact that this is This is gonna be secant. Sec phi is equal to epsilon over, actually no, I should just go for cosine. Cosine phi is equal to square root of epsilon squared minus sine squared theta over 2 divided by epsilon. Yeah. And so if we differentiate this, this left-hand side with respect to phi, we're going to end up with cos phi is going to become negative sine phi times d phi over d theta is going to be equal to, now I have to differentiate this side. It's equal to differentiating, epsilon is constant, so I'm going to pull it out. Epsilon is constant with respect to theta, so I could pull it out. It's not constant like in general, but with respect to theta it is. Now I have to take that that derivative, which is going to be equal to 1 over epsilon naught times, I'm going to pack that, I'm going to call, let beta equals to sine theta over 2. So that would be d by d theta square root of epsilon squared subtracted by beta squared, which is going to be equal to 1 over epsilon. My brain is not braining very well right now because I don't know, I'm a little tired. I didn't have much sleep earlier today. So now we have d by d beta of square root epsilon squared minus beta squared. Okay. Hold on. I'm cooking. Hold on. I didn't do that wrong, did I? It'll work out. It will work out. It's gonna be equal to one over epsilon. We take that derivative. What are we gonna get? We're gonna get cos of theta over 2 times 1 over 2, and then we have to take that derivative, which is going to turn out to be multiply that by 1 over 2, and then we're going to get 1 over square root of epsilon squared minus beta squared, and we multiply that by negative 2 beta. Yeah, I think that's right. It should be. I think that is right. And so we get 1 over epsilon times 4. No, this one and this one cancel out. So we will end up with sine phi d phi over d theta equals to 1 over 2 cos theta over 2 sine theta over 2 times 1 over square root of epsilon squared minus sine squared theta over 2. Boom, which is, yep, we're close, we're fairly close, I think. No. Shit. Wait. No, we're back. We're good. We're good. You should really be sleeping, especially before work. No, no. There's like before I go to bed. It's the evening for me. Unless you mean like also I just noticed chat. How long have you sent that? How long has it been since you sent that? Okay, whatever. Time to continue. Let's see. Okay, so what we're gonna end up with is sine phi. Sine phi is sine theta over 2 divided by epsilon. And this is d phi by d theta. It's equal to 1/2 times 1 over epsilon times cos of theta over 2 divided by square root of epsilon squared minus sine squared theta over 2. Boop. Now what? There's also sine theta over 2 over here as well, which cancels out with this, which gives us d theta equals to 1/2 square root of epsilon squared minus sine squared theta over 2 cos theta over 2 d theta. Woo! Okay. So that means from here, I'm gonna copy paste this to a new page. This page is 21y, 29.7 hi. I got like no sleep before my job today, and it was the worst idea ever, especially given it's a social service job. Yeah, good luck, bro. That sounds like pain, genuinely. So now we can rewrite this to be I did that right, right? I did that right. So that thing becomes 4 square root L over G integral of theta naught to 0. That one becomes 2, right? Yeah, 2 square root of epsilon squared minus sine squared theta over 2. And d theta. Not yet. Just yeah. Mom's calling me for dinner. I have to finish this. Come on, guys. We can do this, right? Oh my god. This one's actually... I'm building armor and I can't stop until it's finished. Oh yeah, I've heard of that. You made like... You're making like a pretty cool armor. Or something. Which honestly sounds cool. Sounds sick as hell. Boop. Square root of L over G. Integrate that. Boop, boop, boop. So we have 1 over cos theta over 2, and that's gonna be d phi. Well, that was monstrous. That was insane. Listen to your mother, she's probably lovely. No, I have to finish my homework first. Yeah, I'm sure it'll be fine. I don't need to eat right now. But now we know that this one becomes pi over 2. This one becomes pi over 2. The bounds. Yeah. Okay. Okay. Now, how do we rewrite this such that we get the form in this equation? That is, we have to find a way to make, we have to find a way such that, to write it such that cos theta over 2 must be equal to square root must be equal to square root of 1 minus epsilon squared sine squared phi. Can we prove that to be true? Where do you live? I assume you were one of those Americans. Oh no, I'm not in America. I am in Thailand, in Asia. Which would be like 6 hours behind me. I think I'm like 4 hours ahead of you, I think. Okay. So now we revisit our triangle here. And we do know that, give me a sec. Oh, wait. Okay. So cos theta over 2 here is equal to square root of 1 minus sine squared theta over 2. Yeah, okay. And so it's equal to square root of 1 minus sine of, oh yes, 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 we got it. We got it. Sine squared theta. And therefore this one equals to 4 square root L over G pi over 2 0 1 square root of 1 minus epsilon squared sine squared phi d phi. And that got us our, yes, yes, I'm in Thailand, yes. And that got us our answer. Yes, yes. That's part 3. Part 3 of the 4 parts of the first question. Anyway, the remaining questions aren't too hard, I think. Oh. Okay. All right. So that's that. We have successfully shown that. Why is the cat here? Why is the cat in here? Okay, whatever. Alright, so that's done. Next up, we have to prove that as for very small theta naught, show that t equals the square root of L over G. Right? That's the question, right? No, 2 pi. 2 pi L over G. Alright, well, let's do that. Should be simple now. Because if this guy is very small, then sine of theta naught over 2 is approximately theta naught over 2. Because of, obviously, that is true. And we have to fucking integrate that? Nah. Nah, no way we do. No way we have to do that. So we're gonna end up with 4 square root of L over G, integrating this, and this becomes 1. Oh, but if it's very small, then epsilon squared is also very small. So this would just become 0. You can approximate it to be 0. The phi. Therefore, we're going to end up with 4 square root of L times pi over 2, which is equal to 2 pi square root L over G. Let's go! I'm on a fucking roll! Okay, that is so satisfying, finally getting it, right? Okay. So that's our final question of the first big question. Onwards to the next sub-question. The noise power spectral density can be approximated by the Planck formula. This one should be fairly straightforward, I think, because we're just doing some approximations. 21 and 29.7. Boop, we paste that there, keep the canvas size, thank you. And then we shrink this down. Noise power spectral density in the thermal noise regime show that KBT is the dominant one. Alright, so let's just do that. Should be fairly simple. I'll message you more information of my beautiful, glorious, and diva armor later. Bye. Alright, see ya, Bluesy. Hello, Asa. Welcome to the stream. I'm so close to being done with these questions. Oh, I'm so goated. I'm such a goat. Yeah. Alright, in the thermal noise regime, KBT is much higher than HF. So that means 1, KBT is much higher than HF, which means that KBT over which means that HF. Are you winning or something? I'm very much winning. HF over KBT. I just solved this problem. I just solved this upper problem single-handedly. I soloed this shit. Yay. Cause like okay, I have to like ego myself a little bit because this this question, this homework, the professor said that we would need some help from a graduate student. That's wonderful. Yup. We would need help from a graduate student, but I soloed this shit. I did not need help. I soloed it. I am a god. Alright. So this would mean that this is gonna be much smaller than 1. I see, you're very smart. Absolutely. And so from this we can approximate that e to the hf over kbt is approximately equal to 1 plus hf over kbt. This is a very common approximation there's a very common approximation technique. Basically, e to the x is approximately equal to 1 plus x for x is very, very small. You can see that this is true when you use desmos.com and like zoom in. E to the power of x and compare that to 1 plus x. You can see that in the as you get closer to 1, as the input x gets closer, these two lines gets closer and closer and closer. I don't understand, but I'm gonna support you regardless. Thank you very much. But yeah, as you get closer and closer, these two values becomes approximately equal. And so we can, so this justifies this equation. And therefore, HF over, what's it? HF over e to the HF over kBT minus 1 is approximately equal to HF over hf over kBt, which is equal to just kBt, because these two cancel out. kBt is just a Boltzmann constant, so kb is a Boltzmann constant, T is the temperature. And so now we have kBt. And therefore, S is going to be equal to S, which is equal to hf plus hf, Planck constant, times the stuff. I don't even know what is going on, but like, there's just a math class, so I'm just doing math, not physics anymore. So this one just becomes hf plus kBt. But because kBt is much higher than hf, you can kind of approximate it to be just kBt, because this guy is so small that it doesn't dent this guy. Have you eaten yet? I have not. Remember to drink water. I should, yes. I have not. My mom is calling me for dinner, so I might as well finish these 3 questions as soon as possible and then end the stream. But yeah. Next up, in the quantum noise regime, where hf is much bigger than kBt, we have to show that thing as a thing. Alright, take a break. I'll do it, trust me. Alright, so number 2, question B. In the quantum noise regime, where kBt is much less than hf, we know that e to the hf over kBt tends towards infinity. Because it tends towards infinity, it means that hf over e to the hf divided by kBt minus 1 should tend towards 0. Because down here, this value approaches infinity, you subtract it by 1, it doesn't really matter. So down here it just becomes a very big number approaching infinity, which is very big compared to hf. So this term approaches 0. And therefore, S is approximately hf. And we got that question done. We are on a roll, baby. Find the transition frequency where thermal noise and quantum noise are approximately equal. What is this transition frequency at T equals to 4.2 Kelvin, for liquid helium? Alright, so for them to be approximately equal, what does that mean? For them to be approximately equal, what's the transition frequency? For them to be approximately equal, sorry, let me think. Thermal noise and quantum noise are approximately equal, but what part is the thermal noise? I'm gonna assume that it's this one. Is it? Wait, noise power spectral density. Noise power spectral density. I should check that. Okay, did I complete? I forgot to turn off the Desmos thing. Anyway, guys, so this is, question 1. Question 1, we approximated E to be approximately that, which we subtracted, and we got that this second term is kBt. And because kBt is much larger than this guy, all of that becomes just kBt, approximately. I completely forgot to turn off the Desmos thing. For this question, the second question, hf is much bigger than kBt, which means this exponential part goes to infinity. Which means down here, the value down here goes to infinity, and because the value up here is not infinite, altogether they become 0. So this whole term becomes 0, so all the remaining thing is just hf. And that's how we got B. And now on to the last bit, we have to find C, the translation frequency where thermal noise and quantum noise are approximately equal. I'm gonna Google the answer just in case so I could check. Translation frequency. Frequency of liquid helium. Is that the right word for quantum noise? I don't think that's the right thing. Okay, whatever. Let's see. Okay, let's see. If for them to be equal, I'm gonna guess that it means that HF is approximately equal to HF over e to the HF over kBT minus 1. I'm guessing. Unless it's actually like very easy, because like unless the professor just wants us to do like kBT equals to HF, and then we know these, we know H, so we just find F. Unless that's what he wanted us to do, which is not impossible, but I think it's too easy. So I'm just gonna think that it's gonna be this one, which means that e to the HF over kBT is equal to 2, which means that HF over kBT is equal to natural log of 2, and therefore the frequency is going to be equal to kBT over H times the natural log of 2. And now I plug that into my calculator. You're doing a great job, Nat. Thank you. Thank you very much. Now we find Planck's constant. I think I'm gonna take this as an answer because I want to go to have my dinner now. Planck's constant is that. Let me just share my. Okay, Planck's constant is 6.62 times 10 to the negative 34. 6.62 times 10 to the negative 34. It's gonna be that. This is the Planck's constant. KB here is the Boltzmann's constant. I don't think I remember what it is. I think something to the power of 23. Boltzmann constant. KB, yeah, is equal to 1.38 times 10 to the negative 23. 1.38 times 10 to the negative 23. And we get that. So now we just plug it in. F equals to, oh, I just had a deja vu for some reason. Okay, it's still going. The deja vu is still going. So now F is going to be equal to KB times the temperature. In our case, the temperature is equal to 4.2 Kelvin. And then divide that by H. And then we multiply that by the natural log of 2. And now we have our answer. That is the translational frequency. And that is going to be it. 6.06 times 10 to the 10 hertz. We got it! Guys, we got it! Yay! I finally finished my homework. Alright, I have to go have my dinner now. See you guys. Subscribe if you liked. Yeah, I'll be streaming more when I have more homework, and also I'm gonna be like working on other projects. So yeah, see you guys. We hit a 3. We hit. I've been streaming for 3 hours. Okay. All right. Goodbye. See you next stream or next video if I do drop the video first. Bye. Yeah. Have a great day. And don't forget to do your homework as well. Yeah.